Welcome back to the deep dive. Today, we're getting into something that's, well, it's everywhere, but maybe not always obvious. Composites.
Mm-hmm.
We're talking about materials that are, deliberately engineered, combining different stuff to get something way better than the individual parts.
Right. It's smart blending.
Exactly.
Yeah.
Intelligent design to unlock new levels of performance.
And what's really fascinating is seeing this level of engineering in, like, everyday things. Or maybe not so everyday. Think about a high-performance snow ski.
Oh, yeah. Like, what's going on inside one of those?
Okay, so if you sliced it open, it's amazing. You've got layers, a tough polymer on top so it doesn't chip easily.
Right.
Then underneath, these fiber-reinforced layers could be glass, aramid, carbon fibers forming what they call a torsion box. That's how they actually tune the ski's flex.
Tuning it?
Yeah. Then there's the core, usually wood laminates or foam. That's the main bulk. More glass fibers for stiffness along the length, and a layer of rubber to soak up vibrations. Plus, you need those sharp carbon steel edges for grip, right?
Of course.
And the base, the part touching the snow. That's a special polyethylene for super low friction and wear resistance.
Wow. So you're saying no single material could do all that?
Not a chance. It's the combination that makes it work.
And that's really our focus today, isn't it? Understanding composites as this whole separate class of materials. It's not just random mixing. It's this principle of combined action.
That's the key phrase.
Getting property combinations you just can't achieve with, a standard metal or a ceramic or a polymer on its own.
Precisely. And technically, a composite is an artificially made material. It's got multiple phases, components that stay chemically distinct with a clear boundary and interface between them.
Okay, so distinct phases.
Right. And you've basically got two main parts.
Mm-hmm.
The matrix, which is continuous, kind of like the background material.
The binder.
Yeah, like the binder or glue. And then the dispersed phase, which is the reinforcement, could be particles, could be fibers. Gotcha. And the final properties. They depend entirely on what those phases are, how much of each you use, and this is crucial, the geometry of that dispersed phase.
Geometry, like shape.
Shape, size, how it's distributed, which way it's pointing. Imagine mixing around pebbles into concrete versus laying long steel bars in it.
Yeah.
Totally different results, right?
Makes sense. So how are we going to break this down today?
Well, the usual way is to divide them into four main types. We'll look at particle reinforced, then fiber reinforced, which is a huge area,
right?
Then structural composites, and finally we'll touch on the really new stuff, nanocomposites.
Perfect. Let's start with those particle reinforced ones. What does equiaxed mean again?
Equiaxed just means the particles have roughly the same dimension in all directions.
Yeah.
Think tiny spheres or little cubes, not long and thin like fibers.
Okay.
And within particle reinforced, there are kind of two main groups. First, large particle composites.
Large meaning how large?
Well, large enough that their interaction with the matrix is macroscopic. We don't need to think about atoms here. The particles are usually harder and stiffer than the matrix.
Okay.
So they actually restrain the matrix from moving, and they carry some of the load themselves. The bond between them is really important.
And you can predict how stiff these will be.
Yeah, reasonably well. There's this concept called the rule of mixtures that gives you upper and lower bounds for the elastic modulus, the stiffness, based on the stiffness and volume fraction of each part.
So designers have a predictable range to work with.
Exactly. It gives them control. Think about adding carbon black to rubber.
Like in tires.
Exactly like in tires. Carbon black is tiny spherical particles. When you mix them in, the rubber gets way stronger, tougher, more resistant to tearing and abrasion. You'd need a microscope to see the particles, but their effect is huge.
Okay. What else?
Another big one is cermets, ceramic metal composites.
Cermet. Okay.
Yeah. Think about cutting tools for machining really hard metals. The cutting edge might be made of super hard tungsten carbide particles. That's the ceramic, embedded in a tougher metal matrix, like cobalt.
Ah, so the hard bits do the cutting.
Right. And the metal matrix, hold it together, gives it some toughness so it doesn't just shatter.
Clever.
Yeah.
And what about concrete? You mentioned that earlier.
Concrete is a fantastic example of a large particle composite. And it's interesting because both the matrix and the particles are ceramic.
Both ceramic.
Yep. You've got Portland cement as the matrix, then sand as the fine aggregate, and gravel as the coarse aggregate. Add water, and it all binds together.
So the sand and gravel are the particles here.
Essentially, yes. They act as filler, reduce cost, and help with packing density. Getting the mix right is critical, though.
How so?
You need the right proportion so the sand fills the gaps in the gravel, enough cement paste to coat everything and bond it, and crucially, the right amount of water. Too little water, weak bonds. Too much water, you get pores.
Which also weakens it.
Exactly. Reduces strength.
Concrete seems so strong, but does it have weaknesses?
Oh, definitely. Its big weakness is tension. It's great under compression, being squeezed,
Right.
but terrible when you try to pull it apart. Its tensile strength is like only a tenth or even less of its compressive strength. It's brittle in tension.
Okay, so that's why we see steel bars in it. Rebar.
Precisely. That's
Yeah.
reinforced concrete. The steel rebar, or mesh, is embedded to handle the tensile stresses and also helps with shear and compression. Steel's a good match because its thermal expansion is similar to concrete's.
Ah, so they expand and contract together.
Pretty much.
Yeah.
And it bonds well with the cement, especially if the rebar has ridges.
And then there's pre-stressed concrete. How does that work?
Pre-stress is even cleverer. You're intentionally putting the concrete into compression before it even sees any external load
Compressing it. Why?
to counteract its weakness and tension. If it's already squeezed together, any pulling force first has to overcome that initial compression before the concrete even starts to feel tensile stress.
Okay, how do they do that?
Two main ways. Pretensioning. Stretch high-strength steel wires in a mold, pour the concrete, let it harden, then cut the wires. They try to spring back, squeezing the concrete.
Got it.
Post-tensioning. Cast the concrete with tubes running through it. After it hardens, feed wires through the tubes, stretch them with jacks, anchor them, and then pump grout into the tubes.
Very cool. So that covers large particles. What about dispersion-strengthened?
Key difference here is particle size. They're way smaller,
Yeah.
almost on the nanoscale. And the strengthening mechanism is different.
How so?
These tiny particles act like obstacles at the atomic level. They hinder the movement of dislocations, tiny defects in the crystal structure, which makes it harder for the material to deform plastically.
So it increases strength and hardness that way.
Exactly. And a big plus is that this strengthening often holds up really well at high temperatures because the tiny particles are chosen to be stable and not react. Think TD nickel-nickel with tiny thoria particles.
Okay, fascinating. Let's move on to fiber-reinforced composites. You said these are really important technologically.
Hugely important. They offer the potential for incredible specific strength and specific modulus. That's strength or stiffness divided by density. So very strong and stiff for their weight.
And the key is getting the load to the fibers.
Absolutely. The matrix has to effectively transfer the stress to the fibers. That bond between them is critical,
Right.
and fiber length plays a massive role here. There's a concept called the critical fiber length.
Okay. What's critical about it?
Well, imagine pulling on a single fiber embedded in the matrix. The stress isn't uniform along the fiber. It builds up from zero at the ends towards the middle. For the fiber to be fully stressed and carry its maximum load, it needs to be at least this critical length.
So shorter than that, it's not pulling its weight.
Pretty much. If it's shorter than L or C, the critical length, it can't build up to its full potential strength. If it's much longer, say more than 15 times L or C, then it's considered a continuous fiber. And most of its length is carrying the maximum possible stress.
Okay, so length matters. What about how they're arranged? You mentioned spaghetti.
Right. Orientation is key. You can have them all lined up, perfectly parallel, continuous, and aligned. Or they can be short, chopped fibers mixed in randomly. Or short fibers that are still somewhat aligned.
Let's take the continuous and aligned case first. Pulling along the fibers.
Okay, when you load it parallel to the fibers, that's where you see the magic. The fibers, being much stiffer, take up the vast majority of the load, like way more than their volume fraction would suggest.
So they do the heavy lifting.
Totally. We can even predict the composite stiffness in this direction pretty well. It's basically a weighted average of the fiber and matrix stiffness based on their volume fractions.
But what if you pull sideways, perpendicular to the fibers?
That's the downside. The properties are highly anisotropic direction dependent. Pull perpendicular to the fibers and the stiffness drops dramatically. The matrix basically dictates the strength then, and it's much, much weaker.
So super strong one way, much weaker the other way.
Exactly. You have to design with that anisotropy in mind.
What about the randomly oriented short fibers?
With discontinuous, randomly oriented fibers, you lose some of that peak performance you get with aligned continuous fibers. But the big advantage is the properties become much more uniform, isotropic, roughly the same in all directions.
Which is easier to work with sometimes.
Often, yes.
Yeah.
And manufacturing is usually faster and cheaper. You can mold complex shapes more easily. They're still much stronger and stiffer than the unreinforced matrix material, just not as extreme as the aligned continuous ones.
Okay, let's talk about the fibers themselves. Are all fibers created equal?
Not at all. You have whiskers, which are tiny, almost perfect single crystals, incredibly strong, but expensive and tricky to use.
Okay.
Then you have common fibers, which can be glass, carbon, aramid polymers like Kevlar. These are polycrystalline or amorphous,
The workhorses.
pretty much. And then wires, which are typically metals like steel, used in things like tires, usually larger diameter.
And the matrix. We said it binds things, transfers load. What else?
It also protects the fibers from surface damage, like scratches, which can severely weaken them. And it acts as a barrier to stop a crack in one fiber from easily spreading to its neighbors. That strong adhesive bond we mentioned is key for all of this.
Makes sense. So let's focus on polymer matrix composites, PMCs. You said most common.
By far. Polymer resin plus fibers. Fiberglass is the big one. Glass fibers in a polyester or vinyl ester resin. Cheap, easy to make, good strength to weight. Think boats, car bodies, pipes.
But maybe not super high performance.
Right, not extremely stiff, and temperature limits its use. For higher performance, you go to carbon fiber reinforced polymers, CFRPs.
Carbon fiber, that's the really strong stuff.
Yeah, high specific strength, high specific stiffness,
Yeah.
hold up well at higher temperatures,
Yeah.
chemically resistant. You see it in aerospace, high-end sports gear,
Mhm.
fishing rods, golf clubs, bike frames.
And Kevlar, aramid fibers.
Aramid fibers, like Kevlar or Nomex, are polymers too, but with this amazing molecular structure. Rigid molecules aligned along the fiber, strong hydrogen bonds between chains. Incredible strength to weight, especially in tension.
But weaker in compression, you said.
Yeah, that's their main drawback.
Right.
But they're incredibly tough, impact resistant, famous for bulletproof vests, but also used in tires, sporting goods.
Okay, this seems like a good place for that design example you mentioned, the tubular shaft.
Right. This is where it gets really interesting. Imagine you need to design a hollow shaft for, say, a machine. It has specific dimensions, and it needs to resist bending. It can't deflect more than a certain amount under a given load.
Okay, a stiffness requirement.
Exactly. So first you calculate the required stiffness, the elastic modulus needed, based on the geometry and the deflection limit. Let's say we need a modulus of about 69 GPa.
All right.
Now we look at materials. We have data for glass fiber composites and various carbon fiber composites, standard, intermediate, high modulus, in a polymer matrix, probably epoxy. We also know their costs.
So which one works?
Well, we use the rule of mixtures equation for stiffness. We find that glass fiber just isn't stiff enough, even if we cacked in the maximum practical amount of fiber, like 60%.
So glass is out.
Right. But all the carbon fiber options can meet the stiffness requirement, just with different amounts of fiber needed. The higher the fiber modulus, the less fiber volume you need.
So the high modulus carbon is best.
Not so fast. You have to look at the cost. High modulus carbon fiber is way more expensive per kilogram than standard modulus carbon.
The trade-off.
Exactly. When you calculate the total material cost for the shaft using each type of carbon fiber, it turns out the standard modulus carbon fiber option is the cheapest overall.
Even though you need more of it.
Yep. Because its cost per unit mass is so much lower, it outweighs the fact that you need a slightly higher volume fraction. It's a perfect example of how engineering isn't just about performance, it's about performance per dollar.
That's a fantastic illustration. Okay, let's switch matrix materials. Metal matrix composites, MMCs.
Right. Here the matrix is a ductile metal, aluminum alloys, titanium, magnesium, copper alloys.
What are the advantages over polymers?
Higher operating temperatures, definitely. Also non-flammable, resistant to fluids that might degrade polymers. They can offer improved stiffness, strength, abrasion resistance, creep resistance compared to the base metal.
Downsides.
Cost is a big one. They're generally more expensive to produce. And sometimes there can be unwanted chemical reactions between the metal matrix and the reinforcement, especially at high temperatures. That often needs managing with special coatings or matrix alloys.
Where do we see MMCs?
Some automotive uses engine parts, like connecting rods, drive shafts, often using aluminum matrix with ceramic or carbon fibers for wear resistance and lower weight. Aerospace is another key area for things needing dimensional stability and specific thermal properties, like satellite structures or telescope components.
Okay, how about ceramic matrix composites, CMCs? Ceramics are hard and heat resistant, but brittle.
Exactly. Brittleness is the Achilles heel of monolithic ceramics. The main driver for CMCs is to significantly boost their fracture toughness.
Make them less prone to shattering.
Precisely. We're talking increases from maybe 1 to 5 units of toughness for standard ceramic, up to 620 units for a CMC. That's a huge improvement.
How do they achieve that?
Yeah.
How do you toughen a brittle material?
Several clever ways. One is called transformation toughening. It uses tiny particles of a material like partially stabilized zirconia mixed into the main ceramic matrix, say alumina.
A zirconia, okay.
The zirconia is in a sort of unstable crystal structure. When a crack tries to grow through the material, the high stress right at the crack tip triggers these zirconia particles to transform into a different, slightly larger crystal structure.
They expand right at the crack tip.
Yes, and that localized expansion creates compressive stresses that literally squeeze the crack tip closed, stopping it from advancing. It's like the material fights back against the crack.
Wow, that's really neat. Any other ways?
Another common method is whisker toughening. You embed tiny, strong ceramic whiskers, like silicon carbide or silicon nitride, into the matrix.
And they just get in the way of the crack.
They do more than that. They can deflect the crack, making it take a longer, more tortuous path. They can bridge across the crack faces, holding them together. And if the bond isn't perfect, energy gets absorbed when the whiskers pull out of the matrix as the crack opens. All these things make it harder for the crack to propagate.
So CMCs are used where toughness and high temperature are needed.
Exactly. Think high-performance cutting tool inserts for machining really hard metals or components in very hot engines.
Okay, let's talk about carbon composites. Sounds intense.
They are pretty intense. Both the fiber reinforcement and the matrix are carbon, relatively new, very expensive.
What makes them special?
Incredible high-temperature performance. They retain their high strength and stiffness way above 2,000 degrees Celsius, excellent creep resistance, high fracture toughness, and because their thermal expansion is low and conductivity high, they resist thermal shock really well.
What's the catch?
The big one is oxidation. Carbon burns, right? So they're susceptible to degrading in oxygen at high temperatures. Needs protective coatings or use in inert atmospheres.
Where are they used? Sounds like aerospace.
Definitely. Rocket motor nozzles, re-entry vehicle heat shields, also high-performance brakes aircraft, Formula One cars, and molds for hot pressing.
How do you even make a carbon matrix?
It's complex. You start like a PMC, lay up carbon fibers, impregnate with a polymer resin, cure it. Then you heat the whole thing in an inert atmosphere to very high temperatures. This process, pyrolysis, burns off everything from the polymer except the carbon, leaving a carbon matrix.
So you convert the polymer binder into carbon.
Essentially, yes. It often requires multiple cycles of impregnation and pyrolysis to get a dense, strong matrix around the original fibers.
Wow. Okay, what if you mix different types of fibers? You mentioned hybrid composites.
Right. Hybrids use 2 or more different kinds of fibers in the same matrix. Why? To get a better balance of properties, often including cost.
Give me an example.
A really common one is mixing carbon fibers and glass fibers in a polymer resin. Carbon gives you high stiffness and strength, but it's pricey. Glass is much cheaper, but less stiff.
So the hybrid gives you
a good compromise. Better stiffness and strength than all glass, maybe better toughness and impact resistance than all carbon, and potentially a lower overall cost than all carbon. You can tailor the mix for the application.
Interesting. How are these actually manufactured? Getting those fibers aligned and evenly distributed seems crucial.
It is. There are several key processes. Pultrusion is one. Think pulling, not pushing.
Pulling.
Yeah. Continuous fiber bundles, called rovings, are pulled through a bath of liquid thermosetting resin to get impregnated. Then they're pulled through a heated steel die that shapes the cross-section. Could be a rod, a tube, an I-beam, and cures the resin.
So you get continuous lengths of a constant shape.
Exactly. It's automated, efficient for things like beams, decking, ladder rails.
Okay, what else?
There's pre-preg production. Pre-preg stands for pre-impregnated. It's basically fiber reinforcement, usually continuous fibers like carbon or glass that has already been soaked with a resin, typically an epoxy, but only partially cured.
So it's like sticky tape with fibers in it.
Kinda, yeah. It comes on a roll, often with backing paper. The fibers are perfectly aligned. You have to store it cold, usually frozen, to stop the resin from fully curing.
And how do you use it?
You cut shapes from the pre-preg tape and lay them up, layer by layer, onto a mold. You can control the orientation of the fibers in each layer precisely all one way, alternating 0 and 90 degrees, maybe plus minus of 45 degrees. Then the whole assembly is cured under heat and pressure, often in an autoclave.
That sounds like how they make aircraft parts.
It is. Very common for aerospace and high-performance structures where precise fiber alignment is critical. Then there's filament winding.
Winding, like winding thread.
Pretty much. It's used for making hollow shapes, usually cylindrical or spherical. Think pressure tanks, pipes, rocket motor casings. Continuous strands of fiber are fed through a resin bath and then wound onto a rotating mandrel, which is the mold.
And you control the winding pattern.
Absolutely. You can wind circumferentially, helically, at different angles. Controlling the pattern dictates the properties of the final part. After winding, it's cured, and the mandrel is removed.
Lots of different ways to build these things. Let's move to structural composites. These sound like they're designed specifically for load-bearing parts.
They are, generally focused on high stiffness and strength, often with low weight. Two main categories here. First, laminar composites or laminates.
Laminates like layers.
Exactly. Made by stacking thin sheets or plies, often made from pre-preg tape or woven fabric, and bonding them together. Each ply usually has a preferred high-strength direction based on its fiber orientation.
And you stack them strategically.
Right. You can have unidirectional laminates, all plies aligned, cross ply, alternating 0 to 90 degrees, angle ply, alternating plus 45, 45, for example, or multi-directional with several orientations to get more balanced quasi-isotropic properties. That ski we talked about, that's a laminate structure.
Okay. And the second type?
Sandwich panels. They literally like a sandwich.
Okay. Bread, filling bread.
Sort of. You have two thin, stiff, strong outer sheets called faces or skins. These could be metal like aluminum or fiber-reinforced polymer. They carry most of the bending loads.
And the filling?
That's the core. It's much thicker, but very lightweight and relatively low stiffness. Its job is to separate the faces, which dramatically increases the panel's bending stiffness, like in an I-beam, and provides shear strength to stop the faces from sliding past each other.
What's the core made of?
Could be rigid polymer foam, like styrofoam. Could be balsa wood, which is incredibly light but surprisingly strong. Or, very commonly, a honeycomb structure.
Honeycomb, like a beehive.
Exactly like that structure, but made from thin foils of aluminum or special paper or polymers. The hexagonal cells make it incredibly light but very stiff and strong, especially in resisting crushing perpendicular to the faces. Great for shear strength and vibration damping too.
Where are sandwich panels used?
All over. Aircraft wings, fuselages, control surfaces, floors, building panels for walls and roofs, boat hulls and decks, car components. Anywhere you need high stiffness and strength with minimum weight.
This sounds like it leads right into the Boeing 787 example. That plane is famous for using composites, right?
It's the poster child. A genuine revolution in aircraft design. About 50% of the 787's structural weight is composites. Compare that to maybe 10–15% on previous generation jets like the 777.
Just 8%. What's the main benefit?
Lighter weight is huge. That translates directly to about 20% better fuel efficiency, fewer emissions, longer range. But also, composites don't corrode like aluminum, and they handle fatigue differently, potentially reducing maintenance. Plus, they allow for design changes like larger windows and higher cabin pressure and humidity for better passenger comfort.
So what parts are composite?
The big ones. The entire fuselage barrel sections, the wings, the tail structures, primarily continuous carbon fiber epoxy laminates made using that pre-preg tape layup process we discussed, cured in enormous autoclaves.
Making the fuselage in single large sections must save a lot of assembly time.
Huge savings. Boeing estimated it eliminated something like 1,500 aluminum sheets and 50,000 rivets per fuselage compared to traditional methods. Fewer parts, less joining, less weight, better aerodynamics. Even things like the engine nacelles often use sandwich panels, carbon fiber faces, maybe aluminum honeycomb core.
Truly transformative. Okay, last stop on our tour, nanocomposites, tiny particles again.
Yeah, back to the nanoscale. Embedding nanoparticles. Particles with dimensions typically less than 100 nanometers into a matrix material, usually a polymer, but metals and ceramics are being explored too.
Why go so small? What's the advantage?
At the nanoscale, materials can behave differently. The huge increase in surface area relative to volume becomes significant. Quantum effects can even come into play. This means nanoparticles can impart properties that larger particles just can't, even at very low concentrations.
What kind of nanoparticles are we talking about?
Things like nanocarbons, carbon nanotubes, graphene sheets, nanoclays, which are tiny layered silicate minerals, and particulate nanocrystals of inorganic oxides like silica or zirconia.
What's the hard part?
Getting them dispersed evenly. They have a strong tendency to clump together, which negates the benefits. Achieving a good, uniform dispersion within the matrix is a major challenge.
Assuming you can disperse them, what can they do?
Lots of cool stuff. Nanoclays in polymers make fantastic gas barriers for food packaging or even tires, slowing down oxygen or air leakage. Graphene nanocomposites are boosting the performance of lithium-ion batteries.
Better batteries. Nice.
Carbon nanotubes can make polymers electrically conductive, which is vital for preventing static buildup in things like fuel lines. They could also dramatically increase strength and toughness. Some polymer nanocomposites are used in dental fillings. They're strong, wear-resistant, and look natural. Multi-walled carbon nanotubes are used in flame-retardant coatings and added to epoxies for stronger wind turbine blades or sports equipment.
So the applications are really diverse.
Incredibly diverse and growing fast. This is a really hot area of materials research with huge potential across many industries.
Okay, well, that's been an incredible journey through the world of composites. If we had to boil it down, what's the big takeaway?
For me, it's that composites represent a fundamental shift in how we think about materials.
Hmm.
Instead of just finding a single material that mostly works, we're designing materials from the ground up, combining different components to achieve specific, often extraordinary performance goals. It's about overcoming the limitations of monolithic materials through intelligent combination.
Right. It's tailoring materials for the job.
Absolutely. And this raises an important question, I think. Seeing the evolution from ancient concrete reinforced with straw to these incredibly complex nanocomposites today. It just shows the power of this design approach. What other combinations are out there? What haven't we thought of mixing yet that could completely change things again?
That is a great question to leave us with. What's the next revolutionary blend? Thank you for joining us on this deep dive. Hopefully you now have a new appreciation for these amazing materials. Take a look around your shoes, your car, your phone. Chances are composites are playing a vital, often hidden role.